Morning, everybody. Can you hear me? Good. So, as you probably heard, I'm a newcomer of sorts in this group, and I don't know the rules. And the fact that I don't know the rules is very obvious. Everybody put their name down there. I put the chair name, right? Everybody puts acknowledgements. I didn't put acknowledgements. Everybody put the pictures of the students. I don't have enough pictures. So anyway, we'll see how it goes. So every joule counts is the theme. We have to find something, and geothermal everywhere is already copyrighted, so we have to put something else. Nobody has sued me yet for this, so we'll go with that until somebody sues us. The chair name is called Energy Transition for the simple reason that my background, as opposed to the background of my predecessor, Roman Shore, is not in drilling. I am more of a reservoir guy. The best part of my career is spent in looking at fundamentals of multi-phase flow and porous media, which we continue to do. And we have pivoted to some other areas that I'm going to show you a little bit. So this is our group. I can never find them all in one room to take one picture of all of them. So the group is also dynamic. If you look at the names here versus the names in the poster outside, you will see differences. That's because they were done in different weeks. The long and the short of it is we have a lot, and we have to find money to feed them. So if you want to look at the work we're doing and split it into two categories, the one at the top is the fundamentals of unconventional resources, and this is multi-phase flow, heat transfer and mass transfer in porous media. Bulk of the application is in oil and gas, and a smaller portion is in environmental remediation. We are not going to talk about that today. I was instructed not to. So, but some of the posters that you have that are out there are some of the unconventional projects that we're doing. Then I encourage you to go and have a look and maybe talk to us afterwards if you're interested. The project we are going to talk about today is under the title of Energy Harvesting Processes. And this is a consortium which is very interesting because it is a very transdisciplinary group of people that came together that include developers for real estate, power generation companies, oil and gas companies, the geological surveys, and the federal and provincial government, and so on and so forth. So contrary to conventional oil and gas type of consortia, here we have a much larger voice. So what we're looking is primarily geothermal, which is most of the stuff we're going to talk about today, and a little bit of shallow geoenergy exploitation for residential heating. So most of you talked about large-scale simulations and this field and that field and this process and the other process, and most of you have been using CMG stars. CMG stars is a very powerful tool, and it uses correlations and physical property determination based on things that they chose, and we chose to question their choices. And in order for us to do that, we actually have to do some measurements of the physical properties and then pass them on to whoever is interested to put them in their simulators. So the first thing that we need to measure is the thermal conductivity. And the thermal conductivity as well as thermal dispersivity, the difference between the two, conductivity, no flow, dispersivity with flow. If you go into the literature to find correlations about these things, you won't find that many. But if you go to mass transfer, you will see that there is correlations abundance in how to measure mass transfer with diffusion only and with convection. So what we're trying to do is to try and see, can we get same type of correlations for heat transfer as we get for mass transfer? And the classical is, let's see. this, right? Pointer works. So we have a flow dimensionless number, which is the Peclet number. And on the x-axis and on the y-axis, we have the dispersion over diffusion and thermal dispersion versus thermal conductivity. Ideally, these things should give us the same thing. So how are we going to do that? Well, we start with the property of thermal conductivity, and this is the device, steady state method of thermal conductivity. So what we do is we put heat load, we measure temperatures, and then we take the same exercise and we put it in a not so good looking core rig where we have a core holder, and in that core holder we have a porous medium in. For this specific set of experiments it was sandbags. We have a fluid. For this specific case it was water. We inject a different fluid, water again, at different temperatures. We monitor the temperatures until equilibrium is reached. Then we apply heat transfer model to match the temperature distributions, and from there the thermal conductivity or thermal dispersivity value that matches best is the one we're using. So this is what we have done here, and here's the temperature profiles that we're getting. So whether we start with this and we have a packing and we look at what happens in the porous medium, or if we start with this here, which is a concentric tube, so annulus central tubing for circulation of fluid, the same thing applies. We can actually generate these temperature profiles. So for this specific problem, we went to the models that we're generating, and the models that we're generating are generated using COMSOL. So we use COMSOL, we set up the mesh, we set up the equations, we get some predictions, and now we are trying to match, for this specific example, the temperature profiles from the simulator and the experiment. And the ones you see there is the best match we could get, so we go with this. And from there, now we can go back and we can start getting predictions of temperature profiles, loads, and things like that, that you would be interested to see and apply in the macroscopic scale. So this, at this point, is not macroscopic scale yet. Now, okay, so we managed to get something regarding the heat transfer. So we have a tool for us to generate. So how can we combine heat and mass transfer together? And so what we do here, contrary to what most of the people are doing here, we're looking at the micro scale as a starting point, right? So what we have here is we have a set of 5 different patterns that correspond to 5 different geometries of pore space, and we're going to do heat transfer flow calculations and mass transfer flow calculations into those. And again, using COMSOL. So we generate profiles that look like this. You see it going? Yes, very good. And then, because we can back calculate the dispersion versus diffusion and thermal dispersivity versus thermal conductivity, we get those graphs, and they would look like this. So the trend is the same. The numbers do not collapse because there is a geometry effect that we have to take into account. So we take this and we renormalize it to the property itself when we have the dimensionless number, which is the Peclet number, equal to 1. Everything collapses, and we get a plot like that. Okay, we've done that for mass transfer. Sorry. It's between my glasses and not my glasses, so it's a little bit confusing. And now it's for heat transfer, exactly the same thing. We have the profiles. From the profiles, we generate these. We look at these. They have the same trend, but they not collapse. We do the same normalization, and we end up with everything being normalized. How nice. So then we go and put everything together. So if you put everything together, and then you will see that there is a shift between heat transfer and mass transfer, but the trend is the same. Which means if we can generate enough of those on different geometries and we get these shift factors, we can translate mass transfer data to heat transfer data and vice versa. So this is work by Shahab, who is a PhD student, and he is abandoning us to go on internship. This is my big problem nowadays. My students find a lot more money before they finish their degree. I will lament on that later. So the previous properties were measured in sands and unconsolidated and consolidated sands for the purpose of looking at geothermal applications. However, for residential heating and cooling, we're looking more at soil. Soil can be sandy soil or not sandy soil, and can be loamy, and there can be all kinds of other definitions. And it has similar thermal properties, but not exactly the same as sand. So we need to measure them. So there is a project in Calgary where we have a residential development that will use geoenergy as part of the heating and cooling of, they started with about 100 units, and then they have some shopping plazas, and then they're going to go to 3,000 units and so on and so forth. So there is a plan for greater implementation, and it's all in the southwest of the city for those of you who are interested. So these guys supply us with soil samples. So they send us the soil samples, and we need to more or less repack those soil samples at a load that is not too excessive to maintain the porosity. And because the soil samples are exposed to rainwater, we will have different water content, and we need to know what are the thermal properties at different water content. So we have to generate thermal conductivity measurements at different porosities and different temperatures, thermal conductivity measurements at different temperatures and different saturations. So then you have those, you can put them in some kind of a fitting model or whatever you want to do with it, or give them as tables you can put in your modeling that will do the heat transfer calculations. But over and above that, we have material, grout, that is put inside these little wells that will do the geo-exchange, and those has their own properties as well. And grout 1 from grout 2 don't look the same. Therefore, their properties are not the same. So we have to do the same exercise for those. So we provided them with all this information, and they have integrated that into predictions of what's going to happen with heating and cooling. There is support for this project from one of my colleagues in the Energy Center, the Geothermal Center, and so we help them with that. But what I present to you here is what my students and postdoctorals have done, and this guy, Nader, is postdoctoral fellow who is finishing actually looking for work if anybody's interested. And now we'll go to a little bit of a different stuff. This is one of the projects that actually there is a poster out there, and there are some details of that, and it has to do with wellbore modeling. I put this slide originally for those of you who haven't seen the variable options, but you have already seen, open versus closed, A versus E, and, company A versus company B several times in this summit. So I'm going to just brush it and go into the next one. So I don't know if you guys recognize the pattern, but this is the ever loop 2, I think, 2, right? And so this is being set up in COMSOL. And in COMSOL, you can do very similar things with reservoir simulation software. The add-on is that you can control the equations. So you can put whatever physics you like, and you have some differences in the mathematical approach. So what we have done is we generated the design of the well patterns that looks like this, and then you have the vertical component, and one of them is the cold, the other one is the hot, and then this is, you see how the reservoir around it is like a gigantic boot, right, which is the region of interest within the wells. This gives us half the problem. The other problem is what are we going to do with all that energy when it comes to surface? And so, do we have any process engineers here? Process. Nobody. Okay, good. So I can mouth off whatever I want. All right. So the big process engineering companies use software which is called Aspen HYSYS, and this gives very detailed design of unit operations if you give it the thermodynamic parameters and the physical properties. So one of my students is working on that package. I'll tell you a little bit about that later. But for this specific project, which was run by Said, who is over there, is one of our postdocs, he used an open source process simulation package, which is over there, and it mimics the ORC. And so we get the hot fluid, we pass it through the ORC, we generate powers, and we do some rudimentary calculations of what kind of powers we can generate into electricity and so on and so forth. So we put different loads for short time periods. We haven't modeled anything long term, let alone geological times that some of you guys are playing with. And we can generate the temperature profiles, the flow profiles, the heat transfer inside the boot, which is the formation, and so on and so forth. And of course, you can play with insulation and other things if you want to do that. How am I doing with time? 12 minutes or 12 seconds? 12 minutes. Okay, we have plenty of time. So one of the things that you can calculate is the temperature profiles as a function of time at the effluent, the temperature profiles as a function of time at different locations of the reservoir. You can also introduce, if you want, a continuous heat source, or you can consider your boot as insulated, right? And you can play around with these heat transfer problems. This generates a lot of heat. This is good. We take that heat and we generate power from it. So this is the thermal power that we generate, and this is the electrical power we're generating. So for those who have no experience in that, almost all of the heat power that we're generating, in excess of 80% of that, is lost. So we are bellyaching and agonizing whether our flow rates are going to be 5 kilograms per second or 6 kilograms per second, while 80% of that energy is going to be lost anyway. So the problem, is here. How to make this energy, whether it's electrical energy or thermal energy, used at a higher proportion than what we get now. And this audience, being the downhole people, don't know about it much, right? Including myself. But the surface people, because they rely on the thermodynamic efficiency, and the thermodynamic efficiency of the system cannot be exceeded, have given up on it. And that's the trick. Now, if you look at the profiles are very similar to what Janine talked about last night, right? We start sharp, we drop, we reach plateau. that plateau will also start dropping at some point in time, but conveniently we don't put it in our time performances as of yet. We need to see how is the kickoff. So how to take this wasted heat and do something about it will be, in my opinion, the game changer in this type of processes. We can use that heat as part of regional heating, and that is a smart thing to do, which means that we have to have the generation very close to the consumer, which is in agricultural, residential, industrial, and so on and so forth. And there are some societal issues that need to be dealt with to do this. Noise and, not in my backyard, the usual stuff. So this is an interesting thing that we are kind of following up. Now, going back to downhole, what is very important is for us to be able to map the thermal properties. And there's only two ways to do that, seismic or logging. Seismic and logging do not give you thermal properties directly. Is there a way for us to find information from seismic and logging to actually translate into thermal conductivity? And in this specific case, we're only dealing with logs. Can we have a thermal conductivity log? So this is one project we're working. Ali is the master student who is doing the first groundbreaking steps. And what we do is we set up, again, patterns. For those patterns, we calculate thermal properties using COMSOL, and we also calculate other properties that are equivalent to different log types. And we found that material properties from acoustic measurements correlate well with thermal conductivity, and we got some really cool correlations with granite and quartz type of geometries, dry and saturated. So looks promising. I most likely have something more interesting to give you next year on that. So, some other projects related to this program. We are looking at same thermal conductivity and thermal dispersivity in different type of rock geometries, and Gerag is doing that kind of work. We're looking at use of nanofluids as thermal property enhancements for the fluids that go up and down in the closed loop. And Miriam is looking at these specific nanoparticles that can enhance thermal properties. And we looked at some of the surface stuff. As I told you, what can we do with these plants to make sure that we get more heat out of them? And this is Mohammed Nematolahi's PhD work. And these are all just started, so these guys are not yet on their candidacy level yet, so we're going to be working for a little while on them. Nader, the postdoc that is working on the soil, also spent some time and worked in these thermoelectric generators, which you can take hot streams, pass these hot streams through these material devices and generate electricity. He was very capable of lighting up a Christmas tree. So it can be done. Scaling up to real values is an interesting proposition. There are some companies already looking at that. It's a company out of Cambridge in England. I think it's Cambridge, not Oxford. Anyway, one of the two. And they have done some really interesting stuff. And because, of course, my predecessor, Roman Shor, left for Texas, but not all his students, did the favor to him to finish exactly the same he left. So we have to actually finish some of these projects. And one of the interesting projects that I was also involved in is from Ajesh Trivedi, who's doing his PhD. And we were doing evaluation of drilling efficiency with different drilling tools. and then CAT scan and SEM these drilled pieces to see the shape and deformation of the near drilled hole, if you want, as a function of load and repetitions and so on and so forth. Now, I have a student who tells me that all these things we're doing is a waste of time, and she proceeded to run simulations using stars to get some predictions, and where she continued is that she did economic evaluations. Disclaimer, she's working for an oil company, so take that as you see fit. But one of the things that we proposed was going into thermal plants, SAGD plants, and so on and so forth, and finding out ways to take that heat, whether it's underground or at surface, and harness that heat and use that heat. And so one of the other things that we said we were going to do is look at surface facilities and do the same thing, and looking at conventional oil and gas wells and doing the same thing. So despite the fact that in the conventional oil and gas, there are companies actually now in Canada that are doing this commercially, the simulation shows negative NPV. So if the NPV is negative, unless there is subsidies, nobody's spending money. The other thing that she looked is for the conversion to geothermal for existing oil and gas wells. The cons, including the NPV, are overwhelming the pros, so that doesn't look promising either. So that's the first pass, and this is the pass that people who are not supporting these themes will show. Our job is to make sure that we introduce the proper physics and the proper engineering so the scale will tip on the other side. With that, I would like to thank you all. Here's some more pictures of our people. And you can ask me whatever you want, but I cannot claim that I will answer it.
Thank you, Dr. Kantzas. One quick question from online. I do not see the solid grains in the micro-scale model touching. Is this a realistic approach? I think it's on slide number 8 where you show the...
No, I know exactly what is being talked about.
Yeah.
So there are different geometries that we have used that they are touching. This specific one that we used here, they are not. There is a convergence issue when you have touching grains at single points. We have to have touching surfaces, and this is where we're heading.
Okay. With maybe a minute or so, let me, I guess, compliment you on the fact that one of your projects will be looking at nanofluids, because yesterday when Janine from FA Technologies was talking about, their closed loop for geothermal, obviously the challenge was the lowering of the Julian cost. The other one is the carrier fluid, CO2 potentially, right. But then having some potentially nanoparticles or whatever that can be highly conductive to carry more heat and make it more energy efficient. Just definitely something we should be looking at.
Right. So with we have actually nanofluids, nanoemulsions, and foams that we're looking at with nanoparticles. Most of the applications are on the other side of the fence. The nanofluids for thermal conductivity, actually, there are a large number of publications, so we're going in the same road. That will be one of the problems. The other problems will have to be friction reduction and relative cost of a nanofluid versus, let's say, a synthesized fluid that will have higher thermal conductivity, let's say an ionic liquid of sort or something like that. And then you have to compare availability, cost, and thermal properties.
Great. So yeah, this closes your presentation. Thanks again.